Okay, so I want to explain the code for this perceiver model. I found some really good code from Phil Wang that is in PyTorch, kind of using the perceiver model that was developed by DeepMind. So this is the perceiver model. Here's the paper for it. Yannick has a YouTube channel. He does a very good breakdown. I can tag that here. They just go through the paper. And here's the model in general, but I want to kind of go through the kind of more detail about the code. But I guess just for a general idea of what the model is, you can read this portion here, I think. It says, because we optionally share weights between each instance of the transformer tower, our model can be interpreted as a recurrent network, an RNN, but unrolled in the depth using the same input rather than time. All attention modules in the perceiver are non-causal. We use no mask. The perceiver architecture is illustrated in figure 1. So that's referring back to this figure, which I kind of have here, but an alternative version that's kind of more based in the code that Phil Wang wrote. And I think that is kind of more, I don't know, explains more about what's actually going on is here. And I created this. So we have this per norm layer, which we'll get into what that's doing, but it's just normalization layers. But what you have in here is you have your input data and you have a initialized data that you just create. You break the input into a copy that you make a key and the value. And then the initialized latent array is what you make the query. You pre-norm them both. You pass them into a cross attention. So you're applying attention between those two, or well, those three. But because the query is this smaller latent array, you kind of stay within that dimension within the attention. So it brings down the complexity of the model. Transformers are O of m squared complexity. So if you're using large time series data, which my problem that I use this for is time series data. So I use like these window sizes of like 500, which can be very hard for training a kind of a deep transformer model. But anyway, you stay in this kind of low dimension because of this. That's what comes out of here. Here represents an add norm. So you pass a copy of before, and then after the cross attention, you add them together. And then you make another copy that goes this way. And one copy comes this way. Another pre-normalization, and then a feed forward. I'll go through exactly what that is. Same thing again here. And then you have a latent transformer. So this is like a self-attention. So here you pass the query, the key, and the value as this latent array. So it's again this small dimension. And then you do the same sort of addition, pre-norm, and feed forward. Now the interesting thing about this is you can repeat this as many times as you want. That's this self per cross attention flag. So if you have this as 2, you would just repeat this one more time. And also the interesting thing is you have another flag for depth. So you can actually repeat the entire block. So let's say if we had this as 2, it would just be 2 of these stacked on top of each other. And then if you had a depth of 2, you'd feed the input back around and come all the way back through. And then you'd re-input the data again. So it gets to see the data again. So that's where the recurrent kind of comes from. Anyway, we can just get right into the code. So here's the input data. So this is the data that you're trying to predict on. This is some random initialization of a latent array that you choose the size of. You normalize both of them. And then the code that we're going to go through uses this pre-norm. It can be a little bit confusing. The way it's done is that it passes a function and then it does some sort of normalization. So you can see here it normalizes X. And then if you do pass a context, meaning that's kind of like the query key, or for our kind of example, it would be the actual data, not the latent array. Then you normalize that as well. But if you're not passing that, then you don't. But after normalization, you apply some function that you also pass into this class. And I'll talk about how that kind of works later on. But then I want to go over kind of some differences that they use in their attention module here. One thing that's kind of interesting is they have no, I think I don't want to go too in depth about, the intricacies of multi-headed attention. I think that's been kind of covered in depth, and most people kind of know that. But here we have a linear layer for the query. Typically, you have another one for the key and then another one for a value, so they all have their own. But here they chose to have a shared key and value linear layer, and then they multiply the inner dimension by 2. And then what they do, so let's go to where that's actually applied. So you initialize the number of heads you have, you pass the query through the query original linear layer, you decide if you have a context. If you do have a context, then your context is input data. If not, you just make the context the copy of the x. But if so, we pass the context through here, and then we apply this chunk. So what you do is they have their inner dimension times 2. So typically you would have a key and a value that both have this inner dimension but not multiplied by 2. But then they do have one, just a single one that's multiplied by 2, and then they apply chunk and then break it apart. So I'm not exactly sure or not exactly sold on the benefit of adding them together, whether that's a time complexity thing. I'm not exactly sure. I think I need to spend a little bit more time thinking about that, but I can just show you what this chunk function does. So if you have something like this, some tensor created that is a 2x4, you apply chunk across the last dimension. In this case would be a 4. And you have 2 chunks. It just breaks it into 2 equal parts. So this is your original tensor. This is your first chunk. So it's just this portion here. Well, I can't highlight that, but this portion here. And then the second chunk is this portion here. So that's all it's doing here. I don't know exactly why they chose to do it this way. Seems a bit odd. But moving on. So the other thing is here they use a rearrange. So this is from the inops library. And you can see it in the full code that I link here. It's here as well. But I also have it listed at the top of this here if you go to the PyTorch code. But anyway, they use inops rearrange. So what it's doing here is you pass it. You tell it there are these shapes. The input shape is actually a 3-dimension that is shaped. This dimension is that dimension. This dimension is that dimension. And then you know that your last dimension is said to be some combination of 2 different numbers, your h and a d. And you want to rearrange it where it looks like this, where you have one dimension here that is this size, and then this size, and then this size. So what you would do here without using this library is you would take your last dimension, you'd divide it by h. That would tell you what your d was. You would assign that size to be here in some sort of reshape, and then this size to be batch size times h. So that's all this is doing. It's a little bit nicer to use. You can kind of use these strings, which can be a little bit more friendly. Although, kind of looking at it, it's a bit more, I think it's actually more confusing looking at it if you haven't used this inops library before. But anyway, moving on. I can actually show you some stuff. So here if you use the inops rearrange, I actually have it doing that. So it rearranges this shape, and you can see if you had an input shape of 2, 2, 4, so it means that this is 2, this is 2, and this is a mix of 2 numbers, so it's probably going to be 2 and 2 if your h size is 2 or your number of groups is 2. And then it rearranges it where this one ends up being the combination, or those 2 multiplied together, and then 2 and 2. It's pretty simple. I also had here to show kind of the differences. This is how you do it in Torch without using the inops library. So it's not too different, but you can just kind of see the differences there. And so I think it's a little more friendly to use this. But anyway, I want to talk about the einsum. So this is another inops thing you may not have seen before. So it gives you some matrix that is size batch I, D, and then another matrix that is batch J, D. So you know that you're doing some sort of matrix multiplication that the dimensions have to match along the D, but these can differ. And then you can get out some output matrix that's going to be a mix of the 2. So that's just the function of kind of doing matrix multiplication, obviously. So you'd end up with something that is Bij. And then you can just use this instead of doing just the matrix multiplication. And I can kind of show what that looks like here. So if we have, let's see, here it is. So if we have a tension that is the shape this, so our tension shape is 222, and then a value shape 223, and then we apply this einsum to it, we're going to end up with a matrix that is 2, 2, 3, and that's because our B is 2, this is our I, and this is our D. So our D ends up, I'm sorry, this is our D. Our D ends up being what is at the end here. So this is the D. And then our I is taken from this matrix and here. So you just kind of see how the shape changes. Here's one with two kind of different shapes that makes it a little more clear. So we have one that is of shape. So this is the tension tensor. It is 2, 4, 2 in shape. And then we have a value tensor that is 2, 2, 1 in shape. So you can see that they match in the batch size, obviously, but then they also have the shape IJ, which would be, for this example, would be 4 and 2. And you see that they match along the J dimension here. And then we output the I, so you can see the J's match, they need a match. And then we output something of BID, so you can see BID. So that's just how you can use this operator, this einsum. Okay. And then not too much different. You have this is your kind of mask before applying the softmax. You apply some sort of softmax. So this is, what do they call this? An attention mask. And then, I guess that's not what you call it before the softmax, but it's the values before applying the softmax, and out of this comes the attention mask. And then we do another einsum operation, reshape it, and then reshape the output again, or rearrange the output. And then you have your output to your dense layer. So that's the tension. And I think we covered a good portion of this. So let's see. The next thing is kind of we're talking about how this kind of section is initialized. So the way that Phil Wang kind of made these was kind of a bit interesting, where it's kind of applied together, rolled together. So since this prenorm I talked about passes a function, you can pass the attention function into it, and this is going to be your cross attention layer. You also going to pass your context, meaning this means that you're going to do cross attention. You also have an input dimension here, so this signifies to your attention module that you're going to be doing cross attention and not just latent attention. So with that, you pass this into the function. It applies normalization to this and this, and then after applying normalization, it passes that information through the attention module, and you get your output here. So that's kind of what's going on here. That's the get cross attention. But we also have the feed forward after that. So that brings you this section right here, does everything here, and then puts it here. You'd have to add, obviously, but then next you want to pass through another pre-norm and then a feed forward. And then here's our feed forward kind of defined here. It's just a linear, then an activation of GLU, and then after the GLU, so this is different than ReLU, and I'll talk about the differences. Then it does another linear layer, and then it has some dropout there. And then you return that, so that is just the feed forward. So it's very simple feed forward, a network that gives you back out your kind of latent array dimensions. And the reason they'd use the GLU, you see it kind of a lot more in transformer architectures now. It's a bit different than ReLU, and ReLU's kind of like the current kind of go-to for almost everything as far as activation functions go. And the ReLU is just, it's flat up until 0, and then has some sort of slope. But the GLU has a bit of negative area here where the ReLU doesn't, and then kind of has a slope up. It's a little bit different. And we also have the ELU. So the GLU has some properties. It's a bit more smooth. It's non-monotonic, meaning that it has that kind of negative relationship. They say that it has better gradient propagation because it doesn't have that cutoff. So most everything that comes from the benefits of the GLU is the smoothness, the smooth shape to it, and then the fact that it doesn't have that abrupt non-negative there. And there are a lot of different kind of approaches to doing this. As you can see, it's like not a huge change, but it can change a lot of your performance. So you can try a bunch of different versions of these. Other ones that are kind of interesting are the swish and mish. And if you look at these, this time ReLU's in red, but the swish and mish are like visually not very different than what you see from the GLU. So it's interesting, you know. It's a little bit of an art into choosing which one you want. So some of it's very kind of, you just have trial and error. AI would probably be better at picking which one to use anyway. But the next thing is the feed forward. So again, you can wrap the per norm. So that's taking us back here. What we're doing is this section here. So we wrap the pre-norm. We pass the latent array. So this time we don't have context, so we don't pass it. We pass feed forward. We pass our latent dimension. So this is just setting up the dimension. So this is like initializing it. So we're not actually passing anything technically, but we're establishing what the layer is going to be that we pass the data through, which is the feed forward in this case for the get cross. So now we have these two things that we can pass data through. We have the get cross attention. We have the get cross feed forward. And then we do the same thing for the latent. This time we don't pass input dimension into the attention layer because this attention layer is just going to do the query, key, and value all the same. So it's self-attention, not cross-attention. Per norm, we only have one thing, so we don't have to pass any context. So that establishes our get attention in a very similar way. And then we do the same thing here, but for the, this is for the latent feed forward. So it's kind of the same kind of initialization as the other for the cross attention, because we're doing what is this block, which is below that the latent transformer. So this is this here. And then this is what the code kind of looks like. So you pass in your data. You have your latents, which is something that is just initialized as x. So this is just some random numbers at the beginning. You have your cross attention that you pass your data into, and then you pass your context data, which is this is your actual data, not randomly initialized stuff. This can be time series information. This can be video. It can be anything along those lines. You pass it into the attention. You add the original latent, because the shape that's going to come out of this cross attention is going to be the same shape as the latent array, and that's your kind of your new x. Then you pass it through the feed forward, so you're getting this kind of add norm sort of thing here. And then after you do your cross attention set, then you move to your self attention, and you see how many of these you have. So this would be determined by how many self attentions per cross attention you have. So this thing can get really deep, and I've noticed just in my own work that the deeper you get it, the better the performance gets. I don't get huge like drops off in performance and like you would see in other things. So I'm kind of really excited about the use of this model. And then what comes out of here is just x. So this is just your latent, and then you can pass it to like a classifier, which is this to logits sort of thing. So you pass it some linear layer that gives you the number of classes. If you want to make it like, you can make it also softmax to get you like a binary class. But But I think this is probably going to be one of the biggest, I think, kind of changes in transformer architecture. I think, everyone knows with ChatGPT and all these kind of adaptations of transformer models. I use a lot of different ones. That this is probably going to be one of the kind of replacement or the next step past convolutional neural network, especially for recurrent task. And I think this solves one of the big problems, which is the time complexity of the size of the attention. So you can kind of make that attention size adjustable. And I really like the kind of recurrent nature of it. So I find this very interesting. I think this is going to make a lot of big changes in transformers, and I think this is going to be adapted in a lot of ways. And one thing that I think is very interesting about this is that this model you can pass time series data to, and then you can kind of change it, just tweak it slightly and adapt it to image data. So the thing about transformers is that they need so much kind of pre-training. So I think there's going to be open fields to kind of cross-training across different data like modalities. So I think if you're like, let's say you're in the space of like brain waves and this sort of thing, I think you could probably take visual images like MRI scans and then also compare that to like time series brain waves. And I imagine the transformer might be able to come up with some stuff that we're not seeing there. So there's a lot of, I think, opportunities for cross-learning using this model. But those are the reasons that I think it's the most important. I also this link will have the code to TensorFlow. For my job, I work in a closed room, so I don't have access to some of these libraries like INOPS because it's like military defense, and we are kind of limited to what packages we can use. So I adapted it to only use TensorFlow, and I don't import any other libraries, but it's the same kind of easily readable code that Phil Wang had, so I'll have that uploaded too.